Hello, everybody, and welcome to lesson 5, which is our current optional lesson for chapter 3, part 3. It is actually section 3.8 from your textbook, the 7th edition one, which is exponential growth and decay. So we are going to be looking at a very particular application of exponential functions where we are talking about a rate of change of some variable y, and it's proportional to the value of y. Y is always a function of time. So our function y, if we have an exponential function, y equals c times e to the kt, if we find the derivative of this, if y is this function here, y prime would be c times e to the kt times k. K and C are just numbers. C is our initial value, and K is called our constant of proportionality, or it can also be called our relative growth rate. Now, if I rearrange this y equals C times e to kt, we will see that this here is the same as this y we started with. So in other words, y prime is equal to y times k, or dy dt, which would be the same as y prime, is equal to ky. What this means is that your original value y is proportional to the rate of change. Okay? So if y is a quantity whose rate of change with respect to time, then y has to be of this form. If we had a different form, we wouldn't get ky when we're done. So y equals c to the kt. C is your initial value. K is your constant of proportionality or your growth rate. Y prime would be your rate of growth. So if you are asked to find your relative growth rate, you're being asked to find K. You're asked to find your rate of growth, you're being asked to find y prime or dy dt. So let's try a question that uses this. Sometimes we won't actually be using the whole dy dt aspect. Sometimes the question will also just tell you that your rate of change is proportional to y, and that is giving you an indication that your equation should be of this form, c e to the kt. So this first question is saying, let y represent the mass in grams of a particular radioactive element whose half-life is 25 years. It's saying how much of 1 gram would be remaining after 15 years. Okay, so what do we know? Well, we know that the half-life is 25 years, and we know that we started with 1 gram. So we know when t equals 0, y is equal to 1 gram. And we want to know when t is 15, what does y equal? Well, we also know that our general form is y equals ce to the kt. So the problem that we have is we know t, we know c, but we don't know k. We need k. So if I plug in all my information I have here, I want to find y. I know c, or my starting value, is 1 gram. I know e is just a number. I don't know k, and I know t for this question is 15. So the problem I have here is I need k first. So in order to find k, we're going to use the half-life information. Okay, so we know that the half-life is 25 years. So we know when t is 25, y would be 0.5 grams. Right? So what this means is I would have 0.5 equals 1 times e to the k times 25. Okay. Or if I ln both sides, I get to bring this k down in front. So if I ln both sides, I would have ln of e to the 25k, or 25k times ln e. And ln e is just 1. That's why I would choose to ln, not log. Okay, so in all these questions, you're going to be using ln here. Now I could divide by 25. If you wanted to plug this into your calculator, you can. I would just keep as many decimal places as possible when you go to plug this back into your equation. So I'd almost leave the answer on the calculator, plug it into the other equation. Okay, so I get negative 0.0277-ish. And now I can go back up to what I wrote in blue and plug my k in. So I had y equals e to the k times 15. So I would choose to just use my exact value. That's my k times 15. I would plug this into my calculator. Again, you're welcome to use the decimal value of k here. So you could have e to the negative 0.0277 times 15. But I would keep as many decimal places as you can. And then you get, if you do either of these, you get 0.660 grams after 15. So we didn't use the new information about dy dt at all, but we're getting comfortable with using e and solving these questions. Most of the time, you will not be given k. You need to find k first, and that's kind of part of the purpose of the question. So we'll try one more on the next page. If you want to try that one on your own first and then go check your answer, you can pause here and then proceed. Otherwise, if you just want to be walked through another question, you can just keep going. All right, so we have 4 months after it discontinued its advertising campaign. This company noticed that its sales had dropped from 1,000 units per month to 80,000 units per month. Okay, so at time is 0, we had 100,000 units per month. And when time is 4, we have 80,000 units. And it says that if the sales follow an exponential pattern of decline, so this is the piece here that is telling us that we're going to need this exponential formula. What will it be after 2 months? Okay, so when t is 2, what is y? Again, if we're following the c equals the kt, we need k in order to proceed. We know c, our starting value, is 100,000 units. We know our t that we're concerned about is 2, but we wouldn't, then that means not know y or k. So we need to use the information about the 80,000 units to find our k. So we're going to use this to find k. So we've got y is 80,000. Our c value is 100,000. E to the k times 4. If I divide both sides, I get 0.8 equals e to the 4k. Since I have an unknown exponent, I need to log both sides. I'm going to ln both sides because of the base e. Then I'm allowed to bring that exponent down. Again, ln e is 1. So I don't need that ln e term anymore, and I can divide both sides by 4. Again, if you'd like, you can plug this into your calculator and you will get approximately negative 0.0558. Now that we have that, we can go back up to this t is 2 months, and we have y equals c, 100,000. e to the k. Again, I like to use the exact value, but you're welcome to use the approximate value if you want. And t here would be 2. If I plug this into my calculator, I get 89,440.19. And this would be units per month after 2 months. Again, we didn't use the dy dt information here, okay? But we are using the y equals c e to the kt. So the last question that we're going to be looking at is called Newton's law of cooling. So the rate of change in the temperature of an object is proportional to the difference, oops, put my box back. It's proportional to the difference between the object's temperature and the temperature of the surrounding air. So it's telling us the rate of change, in this case, d big T for temperature over dt little t for time, is proportional, that's where the k comes from, to the difference between the object's temperature and the temperature of surrounding air. So we know from our previous page, that means this must be y. Now I also know that y must equal e to the kt. Okay? So if I rearrange this, there's a formula that I find a little bit nicer to use, okay? Which is if we have our initial temperature, I'm going to add Ti here is initial temperature. Okay. Temperature of the object, big T, is at time t. Another formula that you can use is big T, the temperature of the object at time t, is equal to the ambient temperature plus initial temperature minus ambient temperature times e to the kt. So what this means is if I were to rearrange this, if I move the first TA to the other side, we would have this T minus TA, that would be our Y, and we'd be left with this little formula here. And so what this tells us is this is our C, our initial value here. So we're going to try a question. This is a hard question that I've given you in these notes here. There's a lot of information. So it says Jackie ordered a latte mocha at Starbucks with a temperature of 95 degrees Celsius. The mocha was transported in a car at 20 degrees Celsius. So this would be my ambient temperature. Okay. After 1 minute, she found the mocha had cooled to 90 degrees Celsius. And it says, how long would it take the mocha to reach a drinkable temperature of 65 degrees Celsius? Okay, so we need to know a couple pieces of information. You can use either sets of equations here. Okay, so if we know that y is equal to t minus ta, okay, my temperature of the object at some time t, I'm going to rewrite this actually as y of t. Then y of 0, my starting temperature would be the temperature of 95 degrees, that would be my big T, minus my ambient temperature 20, which would give me 75 degrees. Right? So this is my C value here. Okay, so if I know that y is proportional, I also know So I know that I have d dt equals k times t minus ta. I know that this would be my y. But I also know that if I have dt dt equals ky, then y must be c e to the kt. So basically what I'm saying is, from the front page, we know that if you have a dy dt where your dy dt is proportional to your original function, so if you have dy dt equals ky, you know that y has to be of the form c e to kt. So my Newton's law of cooling is telling us that y is t minus ta as well. So we have two expressions for y here. We have t minus ta, but we also have c e to the kt. So we're being asked to figure out how long is it going to take it to be a drinkable temperature of 65 degrees, right? That's what we're trying to find. So at 65 degrees Celsius, what is our t, our little t time? That's what we're trying to find out. All we know is that when we start, our y is 75. That's our c value if we're writing this in c e to kt form. Okay. So if I rewrite my y equals c e to the kt, I now have y equals 75 e to the kt. And I want to know, when y is 65, what is t, little t? That's what I'm trying to find out. Now, I don't know k, but I do know another piece of information. I know after a minute, mocha has to 90 degrees Celsius. So after 1 minute, I have 90 degrees, and I know that y1 after a minute would therefore be 7. So I can figure out what t is using this information. Sorry, use k, what k is. So when I do that, I now have 70 equals 75 e to the k times 1, because that's after 1 minute. If I divide both sides, I'm going to have 70 over 75 equals e to the k. I can ln both sides. Again, ln e is just equal to 1. And you can change this ln 70 over 75 to a decimal if you want. Now that we have that, we can figure out when y is 65, sorry, when temperature is 65, sorry, this should be big T. When the temperature is 65, what is my little t? So when the temperature is 65, y would be 45. So I'm going to have 45 equals 75 e to the k, which I, again, like to use the exact value, times t. Then I can solve for t. So if I divide both sides by 75, I'm going to have 45 over 75 equals e ln 70 over 75 times t, ln both sides. Bring the exponent down. Again, ln e is just equal to 1. And then I would have to divide both sides by ln 70 over 75. And so we get that t is approximately 7.404 minutes. So this one's a tough question because the first thing is it gives you no equations, but because we're cooling, we've got this temperature of this coffee that is cooling. We need to use Newton's law of cooling. And there's two pieces of information they give us in Newton's law. One is that we know that T minus TA is our Y, but our Y is also CE to the KT. So notice that when I was talking about a temperature of 65, I didn't plug that in for my Y because Y is not big T. Y is big T minus TA. So I did 65 minus 20. So when I plugged my Y into my equation here, I actually plugged in T minus TA. Okay. So we have two pieces of information. Y is equal to two things. Y is equal to C times e to the kt, and y is also equal to t minus ta. So we had to use the information after a minute to find our k, and then we had to use that to find what our little t is when the big T 65. Now, there is another way of doing this question. I'm just gonna write this down on a new piece of paper here, okay? The other way of doing this question would be to use the TA plus TI minus TA formula that I gave you. So I know my initial temperature. My initial temperature in this question is 95 degrees Celsius. I know my ambient temperature is 20 degrees Celsius. And so if I rewrite this equation, I get 20 plus 95 minus 20 e to the kt, or 20 plus 75 e to the kt. Now you'll notice this 75 e to the kt is the same as what I have here. Where did it go? It's the same as what I have right here. And you'll notice that if I were to rearrange this equation, I can move this TA here. I could move this, oops. I can move this TA over here, and I would end up with T minus TA equals TI minus TA e to the KT, or T minus TA equals 75 KT. And notice how this was our Y and so was this. So the math I'm doing is the same. The steps just look a little different. So if I want to use this other equation that I gave you in the notes, I now have this lovely equation I can use. And so I want to know T is what? I want to know little t when big T is 65. Right? That's what the question's asking me to find. How long would it take, little t time, when the temperature of the mocha is 65 degrees? Now, the problem here is we also don't know K. So I need to find K first. And I'm going to find K using the information that T is 90 degrees when little t is 1 minute. So if I do that, I've got 90 equals 20 plus 75 e to the k times 1. If I subtract 20 from both sides, I get 70 equals 75 e to the k. If I divide both sides by 75, I get 70 over 75 equals e to the k. Ln both sides. Bring the k down. Many of you would do that in one step. Ln e is 1. And then if I want to, I can rewrite this as negative 0.06899. Again, this is the same K we found earlier. My page is getting a little messy. but this is the same K I found here. The same one. No difference. Okay. So the steps look a little bit different, but the math is the same. Okay. Once I have that, then I could go back and find, I've got T equals 20 plus 75 e to the ln of 70 over 75 t. That was a little messy there. Let's fix that up. And I said that t was 65. So I've got 65 equals 20 plus 75 e to the ln 70 over 75 t. I can subtract 20 from both sides. I get 45 equals 75 e to the ln of 70 over 75 t. Divide by 75. Unknown exponent, law on both sides. Bring the exponent down in front. Ln e is 1. Divide both sides by the ln 70 over 75. And plug that into our calculator, and we get that t is approximately 7.404 minutes. So realistically, it doesn't actually matter whether you use this equation or whether you use the combination of information that y is equal to ce to the kt, but also big T minus ta, so both those things. So it doesn't matter which method you use. I can post this as an alternate solution as well. It's the same actual answer. What example is this? Number 3. Okay, so it doesn't actually matter which equation you use. The work will look vastly different. It's the same amount of work roughly. You have to find k first, and then you find p. But really, it's personal preference whether you'd like to use this formula twice, this big T equals formula, or whether you would like to use the bits and pieces that we used here. Either one's fine. Sorry for this giant disaster that is this question, but it's nice and neat in the PDF that's online. That's exponential growth and decay for you.